Right. Well, good evening, class. So today we are having our third tutorial, right? So we'll continue from tutorial 2 questions. Let me do some summary first. So I think by now you all know our style, right? So our style is do some summary first, then go to the question, and then some more summary, then another question. Okay. And also, just to remind everybody, because later on my whole screen is full. So please don't use the chat box, because what you type in the chat, I won't be looking. All right. So if you have questions, you just unmute yourself and ask me verbally. It's okay. And also, you know that from time to time, I like to ask questions, right? So well, please respond. Okay, you just unmute yourself and then you just let me know your answer. Okay, now, yeah. Okay, let's begin. So tonight we'll start with this Poisson distribution. Okay, so it is the second probability distribution that we learn. So let's see what is this Poisson probability distribution. Okay, so we'll first start with this Poisson random variable x. Let me go and get a highlighter. So there's this Poisson random variable x. Now, first of all, we need to know what does it model. Okay, now we need to know what it models. So it actually models the number of rare events observed in a given period of time or in a space. All right, number of rare events observed in a given period of time or space. Right. So let me give you some example. Hey, now this example we actually have it in the lecture notes. Now this is the first one. Okay, the number of rare events observed in a given period of time. All right, so for example, this Poisson random variable x can be the number of girlfriends a guy has during what period of time? From 8 years old until 80 years old. All right, so you see here, these are girlfriends. Girlfriends is like a rare events. Right, so the number of rare events occurring in a given period of time. Okay, from 8 years old until 80 years old. Okay, not yeah. So you remember this thing, then you know you remember Poisson. Right. Now let me give another example. So another example is the number of rare events observed in a given space. All right, in a given space. So this is what we have. So for example, x is the number of pimples on the face. All right. These pimples is like rare events. Yeah. And then this given space is what? It is a face. All right. So you see a face, it's like a given space. Is it or not? Is it okay? So this is a number of rare events in a given space. Okay. So if you remember these two examples, then you will understand Poisson. Okay, not? Then the next thing we come to is that our Poisson, because it is the number of rare events. Number of rare events, right? So how many rare events can there be there? Well, then you know it can be only 0, 1, 2, 3, 4, etc. Right? Yeah. So therefore, we know that Poisson random variable is a discrete random variable. Okay, so we will take values 0, 1, 2, 3, 4, and so on. Okay. All right. Now, since it is a discrete random variable, then you want to talk about the probability mass function. Okay, so this is what we have. Now, first of all, let's look at the notation. Now, we'll use this kind of notation. See the highlighted one, right? So you see this x here, then you see a curly sign, then you see this p and then lambda. All right. So x is the random variable. The lambda is a constant. All right. Now this constant lambda, it actually has a meaning. So what is the meaning there? So the lambda here actually is what? Is the mean. All right. It is the mean rate of the event occurrence. All right. So it is the mean of x. So lambda is actually the mean of x. What is the mean number of events occurring in a given period of time or in a given space? It's okay. Now, so lambda is the mean. And then we have our probability mass function. So this one is a probability of x equal to k. So equal to this expression. You can see that inside got lambda, right? So lambda is a parameter. And then our k, now this k here, now x can take what values? Well, the k here can be 0, 1, 2, 3 until infinity. Okay, so this is the number of rare events possible. Right now, now this formula is inside our exam appendix, so you no need to memorize. Okay, yeah. And point 4 is that just to tell us what is the mean of x, what is the variance of x. So you can see that mean and variance, they are both equal to lambda. Right? Yeah, so that's it. Okay, so now we know Poisson already. So we are ready to go to our first question. This one is our first question. Before we go to the first question, let's look at our most favorite slide here. So our most favorite slide here, it is to tell us, given a probability and statistics question, how do we identify the random variable of interest, right? How to get the random variable. Okay, so that's why it is called what is x. So what is x here? So actually there are two hints. So I actually show this slide last week, right? So in fact, I think I will show for following weeks as well. So the first hint is to look for things like this. Now inside the question, they talk about mean of something, right? Or perhaps it's a variance of something, or maybe standard deviation of something, right? Then that something is what? Is your x. Yeah. Then the second hint here is sometimes they say something has, well, maybe they say has Poisson probability distribution. So we tell you this, that means your x is that thing. Okay, now. And another thing is that when you write down your x, you will write it in a singular form. It's not plural. So for example, you will say x is the height of a student. Okay, you see a student, the height of the student. So it is singular. Okay, now. Okay, so we know how to identify x already. So now we go back to our tutorial. Okay, so here we have our tutorial. So remember our hint, right? Remember how to identify the big X. So let's go and read the question. Okay, let's read the question. Okay, so first of all, we see the number of people who arrive at a cashier's counter in POSB during a specific period of time possesses approximately a Poisson probability distribution. Okay, do you see this one? Something has a Poisson probability distribution. So this is like what? This is like our hint number 2, right? Something has a what? Poisson probability distribution. So what is that thing, right? So let me see. Oh, what is this thing? So this thing is actually, wow, very long, right? Oh, the number of people who arrive at a cashier's counter in POSB during a specific period of time. All right. So although here they never say how long is the time, but they are just giving us a general idea that this one is Poisson. Okay. So is this our x there? Not yet. Not yet. Okay, because here they didn't say what is the period of time. So maybe it will come later. Okay, right. So let's continue reading. Suppose the mean, everyone see this word mean or not? Yeah, the mean number of arrivals per minute for cashier service at POSB. Mean of what? Class, mean of what there? And you see, mean of number of arrivals per minute for cashier service at POSB. It's okay. So mean of what? What mean of this thing? Okay. So what is this mean there? Now this mean is 1 person per minute. Okay. So this second sentence actually give us an idea already. Mean of something, right? So what is this thing? Number of arrivals per minute for cashier service at POSB. So this is likely our x. You see, this long sentence here is likely our x. And we know that the mean is 1. Okay. Yeah. Now let's go and see. Okay, so what is the probability that in maybe let's wait for a minute here. let's go and define our random variable x here. Okay, so over this side, you are looking at the solution. So you see my x is what? X is, you notice that I actually follow this phrase exactly, right? You see, number of arrivals per minute for cashier service at POSB. You see here or not? Number of arrivals per minute for cashier service at POSB. Exactly the same. All right, so this is actually our x. So what do we know? What do we know about this x? Now, first of all, from the first sentence, you already know number of people who arrive at cashier's counter at POSB during a specific period of time is what? Is Poisson. Okay, but now we are more specific. What is that period of time? Class, anyone can tell me from second sentence, what is that specific period of time? Yeah, anyone? Class?
Is it 1?
Huh? One what? 1 year.
One person per minute.
1 minute, because it says per minute, right? So that means the time is 1 minute. So here we know that the time is 1 minute or so we know that our x is Poisson. Okay. Now this one is lambda. This is the place where you put the lambda, right? And what is that lambda? The lambda is 1 because they say the mean is 1, what? And you know that the mean is lambda. All right. So this one here comes from the 1 person per minute. Everybody okay? All right. Yeah. So yes.
Professor,
yeah.
Like so lambda means the means, right?
Yes. Lambda is the mean.
Why don't they use the symbol of mean instead of lambda?
Well, I think in the literature they like to call it lambda. So we also follow. So we also call it lambda.
So lambda mean the same thing, right?
In Poisson, the lambda is the mean.
Okay.
Poisson, yeah. No, not anywhere else, only in Poisson.
Yes, yeah. See, in the context of Poisson and normal distribution, they do mean the same thing. Am I right?
In the Poisson probability distribution, the lambda denotes the mean.
All right.
Okay,
Oh, got it.
All right, Okay, so now we know our x is Poisson. The lambda is 1, right? So we can actually go and write down the probability mass function. So here's the probability mass function. Okay. So now we go and read the question. So where are we? Okay. What is the probability that in a given minute? Okay. So first of all, you note the time frame in a given minute. So the time frame and the time frame in x is the same, right? Yeah. So that means you are still looking at the same x. So in a given minute, the number of arrivals will equal 3 or more. Okay, the number of arrivals means your x will equal 3 or more. Okay, so let's go and find this probability first. So probability that x equal to 3 or more. So what is that like? So that's actually like this. Okay, x greater or equal to 3. Everybody okay? Equal 3 or more. Okay, so we want to find this probability. Now, how do we find this probability? Anyone? How do we find this? What's the meaning? X greater or equal to 3. That means your x can take what values? Any idea?
3 to infinity.
No.
3 to infinity.
Yeah. It's from 3 to infinity. Okay, so that means 3, 4, 5, 6 until infinity. Okay. Yeah, so because until infinity, so you know that we cannot add until infinity. Okay, so this one we cannot do directly. So if we can't do directly, that means you've got to do the complementary event. Okay, complementary event. So what is the complement of x greater or equal to 3?
Anything but 0, 1, or 2.
Anything but 0, 1, or 2. What do you mean?
Meaning that it can't take any values other than the value of x equals to 0, 1, or 2.
Yeah, you're right. Okay. So actually, maybe I elaborate here also. So x greater or equal to 3, right? So the complement is actually x. Now the 3, you got to keep it. Okay, the number 3, you have to keep it. So what you do here is you reverse the sign. Yeah, you just reverse the sign. And then when you reverse the sign that time, you may wonder, right? Do you need an equal here or not? So the equal can only be at one side. So if here already got equal, then this one no more equal. The equal cannot be at both places. Okay, so this is how we do the complementary event. So therefore, this is a 1 minus probability of this. All right, and then from here, we go and interpret that. So if x less than 3 means what now? Because your k is integer, right? So that means 0, 1, 2. That means it's a 0, 1, 2. Is it okay? Yeah, everybody all right or not until here? Now this one, although looks simple, but actually many people can make mistake. All right, so a lot of people can make mistake here. This one can make mistake that maybe someone put an equal sign here. Yeah. And then the next step is also very easily you can make mistake. Why then? Because a lot of people miss out 0. So a lot of people just think that, oh, just 1 and 2 only. So then they miss out 0. So that means then also wrong. Okay. Yeah. So now I point out the common mistake. So you all don't make that mistake. Okay. Okay. Then you just use your probability mass function, then go and calculate. So you just go and calculate. And then you get this answer here. Cannot, yeah. So that's this question. Now let's carry on. Now everybody look at the question here on your left side. Can you tell the bank manager that the number of arrivals, that means your x, will rarely exceed 3 per minute? Every word is important. Can you tell the bank manager that the number of arrivals, that means your x, will rarely exceed 3 per minute? Okay, per minute. First of all, you note the time frame. The time frame is still the same as before, still per minute, right? Yeah, so that means you will still dealing with the same x. Okay, now exceed 3, I think everyone knows exceed 3, right? So then what about this? Rarely exceed 3 per minute. What is the meaning of rarely? Anyone? Rarely means what?
I think it's less likely to occur.
Rarely, is it often?
Of course not.
So actually it's the opposite of often, right? Yeah, opposite of often. Then how do you know rare or not rare?
If not often.
I know it's not often, but how do you tell whether it's rare or not rare? Use what to tell? What should you calculate so that you know rare or not rare?
The probability.
Yes, probability. Because probability, it actually measures the likelihood. How likely is this going to happen? All right, so to know whether rare or not rare, you just go and calculate the probability. Probability that x more than 3. Right, so that's why you see here. To answer this question, whether rare or not rare, you just go and find probability of x more than 3. All right, and then once you find this probability, then you see if the probability is small, probability small means what? Unlikely, right? That means rare. If the probability is big, can you say rare? Then of course cannot. Okay, so we just go and find this. Probability of x more than 3. And once again here, x more than 3, you are going to add to infinity, right? So you cannot do directly. So here you need to take 1 minus probability of the complementary event. Okay, the complementary event. Now, how to write the complementary event? X. And then here, yeah, say you must keep the number 3, right? Then how to put here? How to put here? How to put in this blank?
Smaller or equal.
Smaller or equal, yes. You change the sign, this one bigger, right? Now you change to smaller. And then you see, oh, this one no equal sign. Then you just put here equal. Is it okay? Right, so it's like this, Okay, so that's what I have it here. That's what I have it here. And see, so it's like that. And then this one you can interpret x less than or equal to 3, right? So that means like this, 0, 1, 2, 3. And as I said, this one also people easily can make mistake. In fact, from first step to second step can make mistake. Second step to third step also can make mistake. Okay, but once you have this, then it's just use the probability mass function, then just go and calculate. Okay. So you got your answer here, 0.019. 0.019. Is this a big probability then, class? 0.019 is it big?
No.
It's
Yeah
very
lah.
small.
Yeah,
No.
I know I put here very small, but if I don't put very small, do you think it's big or small?
Small.
I think it's small.
Yeah, I think it's quite small, right? Because the biggest probability is 1. Then this is 0.019, so it's like 1.9%, right? So imagine, say we got a test, okay? 100 marks. Then if someone get 1.9 marks, do you think a lot or not? Then of course very little, right? So this is a very small number. Okay, so very small number. So can you tell the bank manager that this one is rare or not rare? Rare or not?
So super rare.
Rare.
Yeah, it's quite rare. All right. Yeah. So we just say, very small, probability is small. So the number of arrivals will rarely exceed 3 per minute. Okay, now. Okay, so I complete this question or not already. Okay, any problem? Okay.
Prof, I have a question.
So
let's say if you're given like this kind of question, but let's say the probability is maybe like 0.2 or something, how do we consider that it's rare? Is it like less than 0.
Yeah, I
something?
understand what you're
or
saying.
something? Yeah.
Suppose your probability, you calculate it's not 0.019. Suppose you get maybe 0.35. Okay, 0.35. 0.35 is it big or small? You cannot say big, but it's also not say very small, right? Suppose you say 0.35, it's also not very small. So then you cannot say so. All right, so usually this kind of question, they will get a number that is that everyone will agree one, that whether it's big or small. So it won't be something like 0.35, where you can't say it's big, and then you also cannot say it's small. Is it okay?
Okay, thank you, Prof.
Okay.
Thank you, Prof.
All right. Yeah, so let's go to the next one. So pause on. Now we come to another probability distribution. This is the third one that we learned. It's called binomial distribution. Okay. So to talk about binomial distribution, we'll first talk about this binomial experiment. Okay, we first have an experiment and it's called binomial experiment. So this kind of experiment has these properties. All right, so let's go through. So first of all, the experiment has n identical trials, right? Yeah, and then each trial has only 2 possible outcomes. Yeah, so we'll call one outcome success and call the other one failure. Actually, these two here, 2 possible outcomes. The 2 here comes from the word binomial. Bi. You all know bi, right? Oh, you all know bi, bicycle got how many wheels? Hey, class, bicycle got how many
2
wheels?
wheels. 2.
2 wheels.
I mean,
Very
2.
good. Sometimes they tell me bicycle got 3 wheels. Right? Well, that's for children one. So usually bicycle got only 2 wheels. So 2 possible outcomes. All right, every trial has only 2 possible outcomes. And one of them will call success, the other one will call failure. Now notice that this word success, this word failure, is just to differentiate the 2 outcomes. All right, that means success does not literally mean success. Failure does not literally mean failure. Okay, so maybe you will say like, switch on, switch on, switch on, like switch on. Switch on means success. Switch off means failure. Okay, so it has nothing to do with the real meaning of success and failure, just to differentiate the 2 outcomes. Okay, okay, then the third point is that the probability of success of a single trial is equal to P. So there's a small p here, And here just now also got n trials, right? So probability of success of a single trial is p, small p. And the next point is that the trials are independent. Meaning what? Meaning that the success of one trial will not affect the outcome of other trials. Okay, so that's the meaning. And then we got a point E here. So point E here actually talk about what are we interested in this experiment. So we are actually interested in X here, which is the number of successes observed during the n trials. Okay, yeah, this is the X, the number of successes observed during the n trials. And this X is actually our binomial random variable. Okay, so let's repeat. So when you want to talk about binomial random variable, first of all, you need to have a binomial experiment. Okay, so this experiment has n identical trials. And then every trial got only 2 possible outcomes. So you call success failure. All right, probability of success is a small p. The trials are independent. Okay, what are we interested in? We are interested in X. What is this X? You got n trials, right? So X is the number of successes observed during the n trials. Okay, so that's it. Okay, this is our binomial experiment. Okay, real life example. Then, like for example, your quiz. Your quiz is actually a binomial experiment. You say our subject got 400 over students, right? So our experiment consists of 400 over trials. So every one of you is a trial. Okay, so that's our n. And then suppose you are only interested in pass and fail. So there are 2 possible outcomes, right? Pass or fail. And then probability of passing, so maybe we call success as pass. Okay, and probability of passing is P. And then the trials are independent. Of course, when you all do the quiz that time, everyone, you just do your own work, right? You don't go and look at your neighbor's work. Okay, so the trials are independent. And then, of course, we are interested in X. What's X? The number of people who pass the quiz. Okay, the number of successes observed during the n trials. The number of people who pass the quiz. Okay, now, so that's a real life example. So the second point here, we formally define this binomial random variable X. So what does it model? The number of successes observed during n trials of a binomial experiment. Okay, so it's important. Successes observed during n trials of a binomial experiment. So the experiment must be a binomial one. Okay, meaning that every trial can only have 2 outcomes, right? Okay, now the binomial random variable is a discrete random variable. Why discrete? Because it's the number of successes, right? How many successes can you have? 0, 1, 2, 3, 4. Well, at the most until n. So 0, 1, 2, 3, 4 until n. Okay. Now this is our notation. So we say X is binomial, right? So this is how we write it. X is the curly sign, the tilde means is. Then B, B stands for binomial. And then parameters here, you've got 2 parameters, NP. N is what? N trials. The experiment has n trials. Then what is the small p? Probability of success of a single trial. Right? So these are the parameters. And you can see that the n and the p, they are used in the probability mass function. And see, probability of x equal to k equal to this. Okay, and your k is possible values of k are 0, 1, 2, 3 until n. Okay, this time it's not until infinity, it's only until n. Right? All right, now this formula is also given in the exam appendix, so you also no need to memorize. Hey, 0.5 here, the mean of x is NP. The variance of x is NP1 minus P. Is it okay? What is a live transcription? Class, what is this live transcription?
Subtitles.
Subtitle ah? Oh, why you want subtitle eh? Oh, you want subtitle ah? Why do you all want subtitle? Can you give me why do you need subtitle eh? Anyone?
Just in case they cannot understand your accent.
Oh, in case you cannot understand my accent. Okay. All right. Okay, the local people understand my accent, right? Yeah.
Yes, Prof. We understand your accent.
Okay, all right. Yeah, but of course, some of you, well, some of you maybe cannot understand my accent. Yeah. Hey, I think the transcription, the word transcription is very bad. I think I say one thing, but they spell it totally different one. Okay, never mind. So now we go to question. Okay, let's go to the next question. Okay, so once again, we need to look at this slide, right? Remember how to identify the big X, huh? So let's now go and identify the big X. Okay, now suppose you purchase 50,000 electrical switches, and the supplier guarantees that the shipment will contain no more than 0.1% defective. Okay, yeah. And then to check the shipment, you randomly sample 500 switches, you test them, and you find that 4 are defective. Okay, yeah, you find that 4 are defective. I actually don't want to highlight that, so you will find that 4 are defective. Okay, so assuming the supplier's claim is true, you want to compute the mean and the standard deviation. Mean and standard deviation of what? Mean and standard deviation for the number of defectives in a sample of 500 switches. Okay, right. So I think we got our hint now. Can you all see this word mean and this word standard deviation, right? So mean of what? Standard deviation of what? It is the mean and standard deviation of the number of defectives in a sample of 500 switches. So it looks like this one is our X. All right, so let's go and define our X now. So let's go and define our X. Let's see here. X is what? Number of defective switches in a sample of 500 switches. So that's exactly this phrase here, right? Yep. Yeah, I think the transcription is very bad. I think either the transcription is very bad or my pronunciation is very bad. So that they all spell the wrong words. Okay. Anyway, so this is our X. So first of all, let's determine, from what they say, right? Let's determine what is the probability distribution of X. Yeah, what is the probability distribution of X? So this probability distribution of X here, it is what? So far we learn normal, we learn Poisson, we learn binomial, right? Can this be normal? Class, can this be normal? Can this be normal? Can X be a normal random variable?
Yes.
Can
Wait.
Oh, cannot.
Oh, cannot.
Cannot. Why cannot there? Because normal is continuous. It's continuous. But this one is number of defective switches, right? So you know the number is like 0, 1, 2, 3 like that, right? So it's not continuous. Okay, so definitely this one cannot be normal. Can it be Poisson? Can it be Poisson?
I think it's possible.
Cannot be Poisson. Okay, why can't be Poisson? Because you remember that Poisson means what? Poisson means there's a time frame, right? Remember just now your Poisson? Your Poisson is what? is a number of rare events observed in a given period of time or in a given space. But do we have a given period of time here? No. Is there a space here? Also no. All right, so also cannot be Poisson. Is that all right? So cannot be Poisson. So that means, well, you got only one choice left, but it must be binomial. All right, it has to be binomial, and indeed it is binomial. Okay, why you say it is binomial there? Remember what is binomial? The number of successes observed in a binomial experiment. Number of successes observed in a binomial experiment. All right, so our binomial experiment here actually is the 500 switches. All right, 500 switches. Why switch is only two outcomes? What are the two outcomes here? The switch here. Because binomial means only two outcomes, right? One switch can only have two outcomes. What are the two outcomes? Is it a switch on, switch off?
Defective and non-defective.
Yeah. So actually from the context of the question here is defective switch or non-defective switch. All right. And you're interested in the defective switch, because X is the number of defective switches, right? So that means defective switch here means success. Yeah, number of success in 500 trials. Number of success in 500 trials. All right. So your X is binomial NP, your N is 500. What is your small p? Probability of success of a single trial. Probability that a switch is defective. All right, so your small p is probability that switch is defective. And then you see here, the supplier says what? No more than 0.1% defective, right? So you just go and take 0.1% as a small p. Is it okay? All right, so this is your X. Okay, so now we go and handle the first question. You want to compute the mean and standard deviation for X. Okay, earlier on from our summary, you know that the mean of X is NP. Then you just multiply. And variance is NP1 minus P. Then you just take square root, then you get standard deviation. So this is your answer. Okay, now. So we answered this part already. We got the mean and the standard deviation. So let's go and look at the question further. Now, if the supplier's claim is true, so meaning that this 0.1% defective, is it likely? You see, they like to ask this kind of question, right? Is it likely that you have found 4 defective switches in the sample? Because just now they mentioned that you found 4 defective switches. So is it likely that you have found 4 defective switches in the sample? And also, based on this sample, what inference would you make concerning the supplier's guarantee? Okay. Yeah. All right. So let's tackle the first one first. If the supplier's claim is true, is it likely that you have found 4 defective switches in a sample? Hey, how do you know likely or not likely? What to calculate?
Probability.
Probability. Yes, calculate probability. All right, calculate probability of what, Lei? Calculate probability of what? You all say calculate probability, right? Calculate probability of X, big X, number of defective switches in the sample. Calculate probability of what? Is it likely that you have found 4 defective switches in a sample? Calculate probability of X what? What to fill in here?
X equal to 4.
Yeah, yes, you can calculate probability of X equal to 4, which is exactly what they say. This is correct. It's not wrong. Okay. However, if you look at our answer, we actually go and calculate probability of X greater or equal to 4. And of course, you say, hey, why like that? Hey, why like that? Hey, well, that's because this is a more general case. It's a more general case, all right? Because this one actually is a probability of X equal to 4 plus probability of X equal to 5 and plus ... until 500, right? Yeah, probability of x equal to 500. Okay, so actually it's like this. So actually it's a bigger probability. One thing is a bigger probability. And also it includes a more general case. That means not just getting 4 defective switches off. Maybe get 5, get 6, and so on. So it's a more general case. Okay, so therefore we calculate this one. If this probability is small, then your probability of x equal to 4 will even be smaller. Okay, so this is actually a more general case. Yeah, so that's what we are doing here. All right, so I'm going to calculate probability of x greater or equal to 4. Hey, are we going to do this way? Probability of x equal to 4 plus probability of x equal to 5 until probability of x equal to 500.
No.
We are not going to do this way, right? Yeah. So we are going to do complementary event. Okay, so 1 minus probability of x less than 4. Yeah. So you notice the equal sign is only at one side. X less than 4 means what? X less than 4 means 0, 1, 2, 3. Okay, yeah. And then you just because just now we know it's a Poisson already, right? So you can write down the probability mass function. Then you just go and do the calculations here. And and go and substitute inside all. Yeah, click the wrong thing. Right, then you go and substitute inside. And then you get, wow, very small. And this one I think everyone will agree, really very small, right? This is like 0.17%. Okay, so it's really very small, right? So very small. Is it likely? Likely or not? Class, is it likely that you have got 4 defective switches in a sample? Likely or not likely?
Not likely.
Unlikely, very unlikely. Oh, very unlikely. But it actually happens to you. You actually got 4 defective switches. So very unlikely. The probability says very unlikely, but it actually happens to you. So it's like you go and buy lottery and then you get first prize, right? So you know it's very unlikely. All right. So what is the inference? What inference would you make concerning the surprise guarantee? So is it that you calculate wrongly? You go back to see your calculation. Well, everything correct. Your n is 500, right? 500 switches, right? Then your p your p is 0.1%, right? Well, that's also okay. And then why is it that your probability and your, what actually happens, why they differ, right? Why they differ? Then you think that means there's something wrong here. So 500, well, sure it's an okay one. So the only thing here is the supplier's p. This one p, this one 1 minus p, right? Yeah, so all this will affect. So maybe the supplier's p is not correct. So that's why your answer is also wrong, right? So that's your inference, that's what your conclusion is. So therefore, you will say something like that. You say, well, since the probability of getting 4 or above is so small, but it actually happens to you, right? So that means the supplier's claim of this P is most likely not true. Okay. I hope you all are not looking at the transcript, because the transcript I see is very bad. Yeah, I think the transcript is very bad. It's totally different from what I'm saying. So next time I won't have transcript, okay? Because it will just confuse you. Yeah. Okay, any questions here? Okay, no problem, right? Okay, so let's do the next question. Okay, so we are here. So we've done binomial. So the next question is also binomial, but this time we are going to use normal approximation of binomial distribution. So meaning that the real one is binomial, but because it's very hard to calculate, like maybe you need to add many terms, so you want to approximate it by a normal distribution. Okay, so this is how it is. So our x is binomial NP. Now there we need some conditions. Okay, the NP and the N1 minus P both must be greater or equal to 5. So people find that if these two numbers greater or equal to 5, then we can actually approximate x by a normal distribution. Okay. Now normal, the first number is the mean, the second number is the variance. All right. So here you will notice that the mean is NP. We actually match to the original binomial XNP. Okay. And the variance here, we actually match to the original variance. Yeah, makes sense, huh? Yeah. So this is what it is. Huh? So to do this approximation, you first need to check these two. Okay, so it's only when these two conditions are satisfied, then you do the approximation. Okay, right. So let's go and see the next question. My next question, yeah, here. Okay, right. Let me bring the highlighter up. Okay, out of the TV sets sold by an appliance company, 10% require repair before the warranty expires. Right? Now, using the normal approximation to the binomial distribution, so the question actually asks us to do this. Right? So, I mean, once they say this, you already know already. You know that the real one is binomial, but we want to use a normal to approximate it. Okay, so find the probability that the company will have to repair at least 20 of its last 100 sales. Okay, and actually when I read when I read until here, I still have no idea what is our big X. Remember our big X, right? We need to identify the big X, right? So actually until here, I still don't quite know what is the big X. Okay, so, okay, you don't know, right? So just continue reading. Hopefully it will become clearer. So what is the probability that the number of TV sets requiring repair is between 6 and 14 inclusive? Now, this one is clearer. It's clearer to me here. What is the probability that number of TV sets requiring repair? So this is like my X, right? Is between 6 and 14. Make sense? This one make better sense, this one make better sense. So the second part, is like telling us that, you got a 6, then less than or equal to X, then less than or equal to 14. Yeah, look something like this, right? So is this our X there? Is this a number of TV sets requiring repair? Then we also look at the previous question. The previous question say, find the probability that the company will have to repair at least 20 of its last 100 sales. Wow, so now our understanding is, this one is what? At least 20, greater or equal to 20, right? We have to repair at least 20 TV, right? And this 20 TV is, since when one? Is of its last 100 sales. Wow, this one is important. Of its last 100 sales. All right, so actually the second one is also including this, although they never really spell it out, right? Yeah. So this X is the number of TVs requiring repair out of its last 100 sales. So that is the meaning. Okay, now, yeah. So let's go and define our big X. You see our big X is what? Number of TV sets that require repair in the last 100 sales. Right? So I hope everyone is following me, following my reasoning, why this is the X. So our X is what then? Actually, they give us the hint already. It's actually binomial. The original one is binomial. Is this really binomial? Let me think. Binomial is what? Number of successes in a binomial experiment, right? So now this is number of TV sets that require repair in the last 100 sales. In the last 100 TVs that they sold. All right, so obviously your N is 100. Yeah, from this 100 TV, you are interested in what? Number of TV sets that require repair. Okay, so that means number of TV sets that require repair is considered as success. So if this one is success, then what is failure? TV sets require repair means success. So what is failure? Anyone?
It's good TV.
TV sets does not require repair. Okay, so that's the difference. So here success means TV requires repair. Okay, what is the probability that TV requires repair? Well, actually they state here 10%, right? And you see here 10% require repair, right? So the small p here is 10%, so this is our x. Is it okay? All right, Okay, now they ask us to use normal approximation, right? Let's go back to our just now that summary, Okay, you must go and check NP n1 minus p greater or equal to 5 or not. Okay, so let's go and check. Okay, so we check. So we check that both are greater or equal to 5. Okay, so therefore we can use normal distribution to approximate this x. So according to our summary here, our x will be approximated by normal. Okay, and the mean is NP, the variance is NP1 minus P. Right, so it's like this. All right, so later on when you do calculation, we shall use this normal distribution to do the calculation. Is it okay? Okay, y'all. Yep. Okay, now let's go and do summary. Now summary is this. Your original x is binomial, right? But you go and change it to normal, which is a continuous probability distribution. So when you do calculation that time, you also need to make some adjustment. All right. So in our lecture notes now, we say that we are going to use this envelope principle. Now, envelope principle means, see everyone, you can see I draw an envelope here, right? This envelope here. And then inside the envelope, we are going to put what? Put the binomial. Put the binomial x values. So that means the binomial x values, you go and put inside your envelope. Okay. And then the boundary of your envelope will now become your boundary of your probability. All right, so maybe we go and see the next page, then we'll understand better. Okay, but the main thing is your binomial x values, you go and put inside an envelope. Okay. Now, for example, here, envelope principle, right? So first of all, we get the notation correct. This one, first of all, you see this PB. You see subscript B here, right? Subscript B here means that your this x is binomial. Is it okay? Yeah, that means your this x here is binomial. And then you see here there's approximately equal to this Pn, right? This one is PB. Then here you see here Pn, right? Pn means that here your this x is considered as a normal random variable. Just now your that x is a binomial, okay? But when you come here, you consider your x as normal random variable. Okay? Yep. Now you see this probability approximately equal to this probability. Here your x is discrete. This one you can have a probability. But if you also put here, you also put x equal to k, the probability will be 0. Right? Because now your x continuous. So for continuous x, if you put equal k equal to a number, it will just be 0. That probability will just be 0. All right, so you cannot just put like that. You got to give it some kind of interval. Okay, so that's where our envelope principle kicks in. And see that this k, right? K is the what? The original binomial x value. This is your k. I'm going to put inside your envelope. Put inside envelope there, you see? Here's my envelope. Here's my envelope. Now you see your k is envelope inside. Can you all see? That's the meaning of envelope. And then you look at these two numbers. You look at this point here, the boundary here, the boundary here. All right, these two numbers, your envelope, how big can it be? Cannot be too big, plus minus 0.5. Okay, so this number is k minus 0.5, so that is this one. This number is k plus 0.5, so that is this number. So you see, it's the boundary of the envelopes. So same thing here. Next one is x greater or equal to a less than or equal to b. That's your original binomial x value, right? So this is your a, this is your b. So this is your range. All right, so I want to envelope this range. Okay, so you see here, I put one side here and another side here. Okay, so now once again, you see these 2 points. Can you see these 2 points? This point is what? Less than a. How much less than? A minus 0.5. Then this point here, well, it's a little bit more than b, right? How much bigger? B plus 0.5. So always is just 0.5 only. Okay, so this is your new probability lah. Hey, another one, x less than or equal to b. So this is your original x value. So this is your number b here. Less than or equal to b means here. Okay, notice that this one is only one side. Yeah, one side. So it is one side. Then your envelope there is also just one side, just to contain this part. Yeah, just to contain this part. Right, so this is your envelope, and the boundary here is this point. All right, and then you see this point. What is this point? It's more than b, right? So it is b plus 0.5. Okay, yeah. So finally, x greater or equal to a. So this is your a here. Greater or equal to a means this range, right? So this is a one-sided inequality. So your envelope there is also just one side, just to envelope this part. And you can see very well that what is this point here? A little bit below a, right? So this is your a minus 0.5. Okay, now, yeah. So you can understand the diagram. Actually, you no need to memorize. You no need to memorize when do you need to add, when do you need to subtract. Okay. All right, So now let's come back to our tutorial. Just our problem here. Hey, here, right? Yeah. So I say these are the 2 probabilities that we want to find. Yeah. Now our x is approximated by normal. So the first one, PB x greater or equal to 20. So that's this one, right? Yeah. So I want to change to PN. I want my x to be normal, right? So remember your envelope principle. Let's go and draw this. Take a pen to go and draw it. X greater or equal to 20, let's draw the original one. So 20 is here. Greater or equal to 20 meaning what? Meaning all this. All this. So you see it's one-sided, right? How do you draw your envelope? Of course, your envelope also just envelope this part only. Yeah, so this is the boundary of your envelope. This is a boundary. Can you tell me what is this boundary then? What is this number here? Anyone?
19.5.
Yeah, you can see very well from the diagram, right? You don't need to memorize one, right? You can see that this is a PN, x greater than 19.5. Right? X is your normal now. Right? X is your what now? X is your normal. What is it now? Just now, 10, 9. Okay, 10,9. Hey, what happened now? 10,9. Okay, yeah. So now you just go and convert it to standard normal. So your x minus mu over sigma. So this side also x minus mu over sigma. Your 9 is actually the sigma square. So you need to take square root. Okay. Then you just get this. Then you go and change to this because your this statistical table is like that. Okay, so 1 minus 5 of this. Then you really go and check the table. Okay, yep. So it's like this. Okay, Okay, now we look at the next problem. Hey, x greater or equal to 6, less than or equal to 14. So I shall go and draw this range, the original binomial values. So there's a 6 here, there's a 14 here, right? So between them, so this is your range, right? So you want to put your envelope, how to put one here, Put one here. So this is your envelope, envelope this thing, right? So then you know what is this number? What is this number? Right? You can tell me or not these two numbers. What is this number here? What is this number here? Anyone? Yeah, class. What are these two numbers?
5.5 and 14.5.
Yeah, that's right. So you can see very well from the diagram, right? Then just change to standard normal again. Then become like that, right? Then become like this. And this is 5 of upper limit minus 5 of lower limit. Then you just go and check the table. Okay. Yeah, so we complete this question already. Any problem?
Professor,
Yeah.
what happens if you were to use if you were to calculate like normal probability without enveloping principle?
Are you asking me that if I don't put 5.5, 14.5, if I still put a 6 and a 14?
Yeah, yes. What's
Oh,
going
that
to
would be
happen?
wrong. That would be wrong. It will be wrong.
But why? I don't really get it. Why do we need to use the envelope principle?
That is because when you make the approximation, your x is discrete. It's a discrete random variable. But when you approximate it, you approximate it by a continuous random variable. All right. So this one discrete, this one continuous. So therefore, when you want to calculate the probability, for example, here they say probability of x equal to 1. But here you cannot put probability of x equal to 1. Because if you put here probability of x equal to 1, you are going to get 0, which you know that the real one is actually not 0. So you need to make some adjustment. So that adjustment is plus minus 0.5.
But why is it 0.5? Why is not 0.1 or something else?
Well, you see, integers, right? Your 0, 1, 2, 3, 4, you know, the integers. Then between two integers, isn't it? There's like 0.5. So it's in that sense. So therefore, we make it 0.5. Okay, now between two integers, you know, isn't it the midpoint is 0.5?
Yeah, yes.
Yeah, so you take it like, well, kind of reasonable, right?
So basically it makes it more accurate in a sense.
Yeah, it is also more reasonable, right? Because if you put 0.4 or 0.6 like not very logical, but if you put it 0.5, then it's more logical, right?
Okay, so if you're not using the envelope principle, the value will be off, right? Because it's being converted from discrete to continuous, right?
Yeah, correct. So your answer will be wrong.
Okay.
Yeah.
So so does it apply to other distribution as well, or just only in this case?
Only in this case, because here we approximate a discrete one by a continuous one.
All right, thank you.
Okay. All right, so class, let's do some more summary. Yeah. Let's go and do some more summary. Wait, yeah. All right. So now we are going to talk about sample mean and sample variance. And I'm going to do the notations first. Okay, notations. So notations. Let me bring my highlighter. My highlighter. Okay, this mu here, everybody can see this thing, right? This is called mu. Mu, mu, mu. All right. So when you see this notation, it means it's a population mean. All right. It's a constant. Later on, then I give an example to explain about population mean. Okay, not. So now it's just notation. So when you see mu, it means population mean. It's a constant. When you see this sigma square, it means it's a population variance. Well, it's a constant. Then of course, if you take square root there, then you only have sigma, right? this is called what now? This is called population standard deviation. Well, it's also a constant. And then when you see this small n here, well, we always use a small n to denote sample size, the size of a sample. Okay, right. And when we see this x bar here, it's called x bar. Okay, x with a bar on top. This is a capital X bar, right? So this is a sample mean as a random variable. You know, when you see capital letter means random variable. So if you see I write here capital letter, right? So it's a sample mean and you treat it like a random variable. Okay. Now sometimes we also have a small x bar. The small x bar there is a particular value. It's a particular sample mean. Okay. And then when we have this capital S square, capital S square here, right? This capital S square is a sample variance. And if you see I write capital S square means I treat it like a random variable. Okay. Sometimes we also have a small s square. Okay. You see this small s square here, right? This small s square is a particular sample variance. Okay, right. So now I will go to the next example where I will explain about this what sample mean, population mean, this kind of thing. Right, so this is an example. So here we suppose our random variable x is weight of a student, right? Weight of a student, and this student is coming from which population there? So suppose our population is NTU students. All right, so actually the x is weight of a NTU student. Okay, so what is the mean here? What is the mu here? Remember your mu is what? Population mean. Population mean. So it means it's the mean weight of NTU students. Yeah, mean weight of NTU students. So that's the meaning. It's the mean of x. Okay. Then sigma square, we say this is called population variance, right? So it is the variance of x. Variance of weights of NTU students. The mu is mean of x. The sigma square is variance of x. Is it okay? So that's the meaning. We call this population mean, population variance. Then we also have this x bar, right? Yeah, just now we say it's a sample mean, right? So here there's a sample coming in. All right, now suppose your population, NTU students, so many, right? You go and get a sample of n students. You see this n or not? Then our sample size n, yeah. So we go and get a sample of n students. All right, and this x bar is what? Mean weight of this sample. Yeah, mean weight of a sample of n students. All right, and what about our s square? This is our sample variance, right? So that means variance of weights of a sample of n students. Is it okay? All right, so therefore you have sample mean, you have sample variance. Sample mean means mean of a sample. Sample variance means variance of a sample. Right, so here are the examples. Okay, now, so I hope you are clearer now. And I want to go back to explain why sometimes our sample mean, why sometimes it's capital, why sometimes it's a small letter. Similarly, your sample variance, why sometimes you can say it's a random variable, then why sometimes you say that it's a particular value. All right. Well, it's actually quite easy to understand because you see your population, just now your population. I want to go to the next page. Just now your population, NTU students, right? So we say you get a sample of n students. Okay, a sample of n students from this population, right? So wow, NTU students, so many. How many samples can you take? A lot of samples, right? Agree? You can take many samples of n students. One sample will give you one small x bar. One sample will give you a particular x bar. So here your x bar is a small letter. One particular sample will give you one small x bar, right? Then of course another sample will give you another small x bar. Then another sample will give you yet another small x bar, right? So that means your this sample mean actually can take many different values, right? For this sample is this value, for that sample is another value, and so on, right? I'm sure you can imagine that. So how many samples you have? Wow, many samples. So that means your x bar can actually take many different values. So therefore, you can just consider this x bar as a random variable, because random variable can also take many different values. All right, so that's why you have this. You can consider your x bar, capital letter, as a random variable. Okay, well, if you understand this, that means sample variance also the same thing, because this is the variance from a sample, right? So you one sample give you one sample variance. That's your small s square law. Then another sample give you another small s square, right? But you have many samples, right? So that means your small s square, there are different values. So you can just consider it as a capital S square, as a random variable. And then it can take all these different values. Is it okay? All right? Yeah. So that's about sample mean and sample variance. Then the next thing is, now because they are random variables, right? So we can talk about the probability distribution of this random variable. All right? So we'll first look at sample mean as a random variable. Sample mean x bar. Yeah, sample mean x bar. Yeah, so this one is capital X bar. So you treat sample mean as a random variable. Now, it is a random variable. You can talk about the mean of this. You can talk about the variance of this. You can talk about the standard deviation of this. All right, so what is the mean of x bar? It's actually mu. It's actually the population mean. How about the variance? Well, it's actually sigma square over n. Sigma square is the population variance, n is the sample size. Then of course you square root this, then you get the standard deviation. Standard deviation of x bar is sigma over root n. Okay, so this point A here is always true. All right, so the mean of x bar is mu, the variance is sigma square over n, and the standard deviation is sigma over square root n. This one always true. Okay, now let's look at point B. Now point B is, you know something else. You know that your x is normal. Okay, you know this, you know x is normal. Now, if x is normal, it implies that your x bar is also normal. Okay, x normal implies x bar is also normal. And what is the mean there? From point A, the mean is mu. From point A, the variance is sigma square over n. Okay, so this one, x normal implies x bar normal. This holds for any sample size n. All right, here no matter what the n is, whether n is big or small, this one holds. X normal implies x bar is normal. Okay, yeah. And then we come to the third point. Third point is central limit theorem. Wow, this one is very famous, right? So in central limit theorem, you actually do not know your x is normal. So you may not have information about the x. You don't know whether your x is normal or not normal. Okay, maybe totally no information. But here it's very powerful. What it says is that if you have a big sample size, big sample, how big is big? N greater or equal to 30. All right, so if you have a big sample size, then you know that your sample mean will be normal. Okay, will be approximately normally distributed. This is the mean. This is the variance. All right, so this is central limit theorem. And this holds for any big X. That means whether your big X is normal or not normal, doesn't matter. As long as the sample size is big, then you can be sure that your X bar is approximately normal. Right now, so these are point A, B, C, yeah. So we all know the importance, right? Yeah. Okay, all. So everybody okay here? I hope it's okay. Yeah. Yeah. Then what about this sample variance? Now, sample variance, the capital S square is a random variable, right? So what about its distribution? Now, this is the distribution. It is actually a theorem, but this theorem, it doesn't have a name. It's not called central limit theorem or anything, all right? But there's this theorem here in our notes. So it says that if your x is normal, here you need to know that x is normal. That implies that this thing, n-1 s square over sigma square. Then you see s square or not? Then your s square is here, your sample variance. But it's multiplied by a constant. And that constant is n-1 divided by sigma square. It's a constant, right? This particular constant, you multiply s square, well, still a random variable, right? So this random variable is having a chi-square distribution with n-1 degrees of freedom. Right? Chi-square is a probability distribution. All right, it's just another kind of probability distribution. It's a continuous random. It's a continuous probability distribution. Cannot. We actually have a table for it. Maybe I show you the table, Table is here. This one is our chi-square distribution. And see or not, chi-square. You can see that it's a continuous probability distribution. This is the probability density function. Does it look like a bell there? Is it like normal like that? Normal is a bell. Then I also have normal here. This one is normal, right? Normal is a bell, right? This one is not bell. This one is like a slanted one. Okay, a slanted one. I actually call it a wave. It looks like a wave or not, class? This one looks like a wave, right? Have you all been to the wave? Class, have you all been to this the sports hall?
Yes.
You've been to the wave, right? It looks like this, right? So this is called the wave. So this is the probability density function of chi-square. All right. Yep. We'll go to this table later. Okay. Yeah. So now we roughly know about this one already, right? Where are we? We are here. No, we are not here. We are also not here. So okay, I know it's this file. Okay, so this is this theorem, it governs the probability distribution of x squared. So if x is normal, that means n-1 over sigma squared times s squared is going to be a chi-square probability distribution. All right, and we have a chi-square table for it. And for x bar there, these are the 3 points. Okay, yeah. So now with this, we go to our tutorial problem. So we are now in this tutorial. Okay, so let's look at the first one. The weight of a box of cereal has a normal distribution with this mu and this sigma. Okay, so what is having a normal distribution? I think very clear here. It is the weight of a box of cereal. All right, so let me go and define my x. So my x is the weight of a box of cereal. All right, so they tell us that x is normal. The mean mu is 340, right? And then the sigma square is 5 square. Okay, not. Hey, let's look at part A. What is the probability that a randomly selected box will weigh between this and this? Right? So you connect to your x. Your x is a weight of box of cereal, right? So that means you want to find the probability that x is between this and this. Okay, so that's quite clear that you want to find this probability. Yeah, I hope everyone clear. So how to find this probability, right? Well, you already know that your x is normal one. So you just change to standard normal, right? Remember how to change? Change to z, x minus mu over sigma. Then of course you got to do it throughout lah. So you minus the mean, divide by 5, because your sigma here is 5, and here also minus mu over sigma. Everybody okay, right? And just go and get the numbers. And then phi of upper limit minus phi of lower limit. And just go and check the table. Okay, so this one is okay. Yeah, it's very clear, huh? Now let's look at part B. Look at part B, yeah. Part B is different. 10 boxes of cereal. Now you've got 10 boxes. Just now only one box. 10 boxes of cereal are selected at random for weighing. Find the probability that their average weight will be between this and this. All right. Their average weight will be between this and this. This average weight now refers to average weight of what now? Class, this average weight refers average weight of what?
10 boxes.
Box of cereals.
Yeah, 10 boxes of cereal. Okay, so here you can think of these 10 boxes of cereal like a sample of size n. All right, and then this average weight then becomes what? Sample mean. You get it? So we let X bar, capital X bar, be average weight of 10 boxes of cereal. All right. And then of course here you actually want to find probability that this sample mean is between these two numbers. Okay, now. Okay, now let's go and get the this capital X bar. What is the probability distribution, right? Now from part A, you already know that your X is normal, right? X normal implies X bar normal. Okay, you go and type something here. So X is normal, right? You already know that X is normal. X normal implies what? Implies X bar also normal. So this is actually from here, point number B. X normal implies X bar also normal. Okay, so I know that my X bar is normal. This is the mean, and this is the variance, sigma square over n. So you can put in the number. All right, everybody okay here? Okay, okay, let me go and find this probability. How to find? Well, it's just a normal probability, right? You just treat it like a normal random variable. This is the mean, this is the variance, right? So how to change to Z? This is how you change to Z. You go and minus the mean, 340, divide by standard deviation. Where's the standard deviation here? Now, this one is the variance. This is the variance. All right, so if you want standard deviation, take square root. And that will be 5 over root 10. Is it okay? Yeah, class, everybody okay or not?
Yes.
Right? So this is a standard deviation. And after this, you just go and simplify. Then phi of upper limit minus phi of lower limit. And then go and look for the table. All right, everybody okay? Okay, so this one done. So now we go and look at the part C. Okay, part C, this time is 30 boxes of this cereal are selected at random for weighing. All right, so it looks like now our sample size changed, now changed to 30, right? So find the probability that the sample variance is more than this one. Okay, so I think very clear probability that S square more than this. So this is what you want to find. So find probability of S square, capital S square. S square more than this number. All right, now you want to find this. Is it okay? So let's go and find this. So I let S square be a sample variance of 30 boxes of cereal. Okay, of course I want to find probability of S square more than this. So now we go back to our summary. Now there's something about this S square, right? So we say that X is normal implies that this thing is chi-square with n-1 degrees of freedom. All right, do we know X normal or not? In our problem, do we know X normal? Actually, we know, right? From part A, we know that X is normal. Okay, so therefore we can apply this. X is normal. So therefore we know that your n-1 S square over sigma square is chi-square random variable with n-1 degrees of freedom. All right, now of course our n here is 30. Our sample size here is 30. Okay, all right, everybody okay, huh? So now let's proceed to find the probability. Hey, probability of S square more than this. What to do there? Now, what we do here is you somehow need to make it like that. Okay, why you need to make it like that? Because you know that this one is chi-square. All right, so you want to make your S square, you want to make it so. Cannot. So how to make it like that? Well, that's quite easy. You just multiply n minus 1 divided by sigma square. And then it will be like that. And you just multiply n minus 1 over sigma square. Then of course you got to do it to this 36.69 also. So also n minus 1 over sigma square. Right? So you got to do throughout. And then after this, this one now is your chi-square already, right? So this one you don't touch off, because this one is going to be your chi-square. But this right-hand side here, you can put in your numbers, and you can simplify the numbers, right? So you are getting this, right? So actually what you are having here, this is like your, can I type or not? Yeah, I think I can type here. So this is like equal to probability of chi-square. Now I cannot type chi here. My keyboard doesn't have chi, okay? So I will type chi-square. Chi-square, but of course you all know the symbol, chi-square. Yeah, more than 42.56. Okay, yeah. So this is what I have. All right, so this is actually your chi-square. Chi-square with n minus 1 degrees of freedom. All right, now how to find this probability? We'll go to the chi-square table to find. All right, so let's go to the table. This is my table, chi-square table. Everyone has this table, right? And we'll refer to this table in our assignment, in our quiz, in our exam. Okay. All right, let me explain about this table here. Let me bring up this. Okay, everyone can see this number that I underline. Yeah, this is actually chi-square subscript alpha. Chi-square subscript alpha is a symbol. Okay, it's a symbol. This number we write it as chi-square alpha. All right, what's the meaning? The meaning is that this area, that means from this point onwards, this area, this small area here, well, this area has the meaning of probability. It's the probability of chi-square, the random variable, more than this number. More than this number. This number and this number are the same. Okay, probability that chi-square more than this number is this shaded area here. All right, this is the probability. It is this area. And this area is alpha. All right, so that's why now you all know why I put a subscript alpha there. So the subscript actually means that the probability from this point onwards, the area from this point onwards is alpha. All right, that is the meaning. All right, I know that initially you'll find this very strange, but you will get used to it. Okay, so the subscript refers to the area from this point onwards. All right, and it is the probability. Yep. Now look at this table. Now this table here, you notice the heading, percentage points of chi-square distribution. All right. So actually, what is tabulated in the table is that chi-square alpha. Yeah, I don't know how to write. Chi-square subscript. Chi-square subscript alpha is tabulated. Yeah. Chi-square subscript alpha is tabulated, meaning this number, chi-square alpha, are the values that you are seeing here for different alpha. All right, so that's why you see here alpha, right? Can you see alpha 0.99, 0.975, and so on? So these are the different alpha, and this is the chi-square alpha values here. All right, and subject to different degrees of freedom. Yeah, we got something called degrees of freedom. It controls the shape of the graph, right? You see this one is a wave, right? So the wave, I mean the wave, some wave is more like wave, some wave is not so much wave, right? So it's controlled by these degrees of freedom. Yeah, so degrees of freedom here, and then for different values of alpha, the chi-square alpha are tabulated. All right, okay, now coming back to here, our problem is to find probability that chi-square more than 42.56, right? So that means your 42.56 is like your chi-square alpha. It means your 42.56 here is playing the role of chi-square alpha. Your chi-square alpha is like your 42.56. All right, so we just go and find out this number 42.56 from the table, right? Because we know the degrees of freedom. The degrees of freedom here, n-1 is what? Is 29. Okay, 29 degrees of freedom. Yeah, 29 degrees of freedom. So let's go and see the table. 29. Yeah, 29 is here. Yeah, 29 is actually here. And you all see this 29 degrees of freedom. So I use a ruler to underline it. So your chi-square alpha must be a number along this line. And you all see the number 42.56. And you see it is here. And you see 42.56 is along this line. Degrees of freedom 29, right? So 42.56 is there. Yeah, so this is your chi-square alpha. Is your chi-square alpha. So if I ask you what is the alpha? Class, what is the alpha? It's your 42.56, right? Corresponds to what value of alpha?
0.05.
So then you go up and see. Oh, your alpha here is 0.05. Corresponds to this alpha. All right. So therefore, I know already what is my alpha there. My alpha is 0.05. Is that all right? Class, do you follow me? All right, so I go and find the value 42.56, right? Then I found out that alpha is 0.05, right? Then I go and type here, right? So look at this sentence. What do you have? Probability of chi-square more than 42.56 is alpha, and your alpha is 0.05. All right, so that's why our answer here is 0.05. Okay, now class.
Yes.
Any questions?
No.
Okay, very good. That is very good. Okay, so we are back here. Let me go and see your chat. Oh, someone say what big L. Right. All right, so we come.
Sorry, excuse me. Just one question. Because for this distribution, right, there's two graphs. One is the Z one is the chi one. Actually, when do we use the Z graph and when do we use the chi graph based on the question itself?
When do we use?
Hello, guys. Because there's two kinds of graph that we're referring to, right? One is the chi square. One is the one that's refers to the Z.
Someone talking.
I'm streaming right now. Hello, Shiggy, Russian, Table, King of Noobs, Lousy.
Just like for example, previously, right? We were.
Okay, I mute all. Okay, you want to ask me a question, you unmute yourself. Can you unmute? Because just now someone forgot to unmute.
Now we're playing Fortnite now with you guys.
I was asking because previously when we were learning, we were learning about a Z graph. And right now we are learning a chi graph, right?
Yes.
So when do we use the Z? When do we decide to use the chi? Because both of the ways that we approach of solving the question is totally the same. Yeah, so how do we differentiate? When do we use the Z graph? When do we use the chi graph based on the question?
I got your question. You're asking me when do you use Z, when do you use chi-square, right?
Yes.
It depends on the situation. Like for example, here you want to find probability of S square, you know, and then you know that your S square, when you multiply by n minus 1 over sigma square, is related to chi-square. So obviously here you need to use chi-square, right? Make sense?
Yes, yes.
My roomie got a massage chair today. It's like a gaming massage chair. It's not good, but okay. Well, see, that's a one up. Hello, boy. How are you?
Yeah.
Yeah, so in this case, then, okay, so for example, is both graph actually related, is it? It's just that when we use H graph based on what do we have on the unknown.
Yes, it depends on what you have. Like for example, here, this one is a normal distribution, right?
Yes.
So obviously you want to use the normal table. Okay, you won't want to go and use chi-square, right?
But chi also have a normal, right?
Because without you
Yeah,
guys,
then both also got normal.
Someone
but now that I'm streaming, I'm actually gonna have a good day. I can feel it. Animated email to someone I know, right? Oh, Jello, you didn't have a good day too. Yeah, I feel it.
Hey, Evangeline, your background noise damn jialat.
Okay.
Okay.
Hi, Prof. I think I know what's her question. I think her question is that based on the question given, right? When do we know when to use the chi graph or when do we use the P graph? So for example, there's a question given. So when do we like differentiate which graph to use?
As I say, it depends on the question. Then, like for example, just now our part A, we know that X is normal, right? So then you know that you need to find this probability. Then you know that because your X is normal, certainly here you need to use your this Z, right? Yeah. I mean, you won't from here go and use the chi-square, right? Because it doesn't make sense, what? Correct or not?
So does it mean that for normal we will use the Z graph? Like the
yes.
of Z?
For normal probabilities, you only have your standard normal table. For normal probabilities, you only have your standard normal table. So anything involving normal probability, you need to change to Z. Because if you don't change to Z, you can't use this table. And that's the only table that we have. That's why it's called standard normal. Standard, that means everything not standard one must change to this standard one.
Okay, sorry, wait. Because that's why you say normal, then we will use the Z graph. But then for this question, right, it's normal distribution, then we are using the chi graph, is it?
No, we only use the chi-square in part C. In part C, we are using the chi-square because here our S square is related to chi-square random variable. So that's why you need to make use of the chi-square, the chi-square table. So you must see what you are finding. Here you don't have anything normal. Your S square is not related to normal, okay? But it is related to chi-square. So of course you need to use the chi-square table, right? Make sense or not?
Yeah.
That means you must see what is the related distribution. Then of course you want to use the related one, right?
Yeah.
So it's just like that, oh. That means when you need to use what, it all depends on at that time the probability that you want to find, the distribution, is it normal? If normal, then use normal table. If chi-square, then use chi-square table. It seems a very natural thing to do, right? It won't be that your probability is a normal one, then you go and use chi-square, right? Or if it's a chi-square one, then you go and use a normal one. Then isn't it like a mismatch like that? Yeah. Okay, all.
Yeah, can. Thanks, Prof.
Okay. Yeah. Okay. So no more questions. So we'll meet next week lah. So next week is after Chinese New Year, huh? Okay, now.
Okay, thanks, Prof.
Okay. Yeah, good night.
Happy New Year. 画啦。
Oh, Happy New
Thank you,
Year.
Prof.
Okay, bye-bye.